you have cascade refrigeration system. You know how to analyze the compressor, condenser, flow-through expansion valve. There's a compressor, expansion valve, evaporator. Only really a challenge when you put two refrigeration systems together like this, so that it sort of pumps the heat up one level, then pumps the heat up another level to dispose of it at a high temperature and pick it up at a low temperature, is the heat exchanger. So you do an energy balance around this heat exchanger. The direction of the heat transfer is from the cycle A, the low temperature cycle. This acts as a condenser, doesn't it? And so it's going to be rejecting heat, transferring heat to the fluid in cycle B, where this heat exchanger acts as the evaporator. And so the Q dot from the fluid in cycle A is equal to the Q dot into the fluid in cycle B. That's the energy balance. That energy balance is the mass flow rate of the fluid in cycle A, mass flow rate cycle A, times the enthalpy 2 minus enthalpy 3. It's higher enthalpy 2 because this acts as a condenser. It's coming out typically saturated liquid at state 3, going in superheated vapor at state 2. And then that's equal to the mass flow rate in cycle B times the change in enthalpy. Here, it acts as an evaporator. What enthalpy is higher? 5 instead of 8. So everything's positive the way I wrote it. So that's what comes out of A goes into B. And there it is. It links them together. Now you can solve that system. Any questions? They commonly report the performance of common pieces of equipment: refrigerators, room air conditioners, central air conditioning systems, heat pump systems, furnaces. For a what they call a room air conditioner, that would be something like a window unit instead of a central unit. They have the energy efficiencies reported in a EER, energy efficiency ratio. And this EER is a ratio of the amount of cooling or cooling capacity, how much cooling or rate of cooling in BTUs per hour, divided by the energy efficiency ratio is the rate of cooling in BTUs per hour, divided by the power input, here W dot electric, into the system in units of watts. So it's power over power, but the units don't make it go. Well, you can see the range for room air conditioners, sometimes 8, 9, 10, somewhere in there, in that region, is the EER. Well, hold it. We studied a metric that was just like this. What did we study? We studied the coefficient of performance for a refrigeration system, which was Q dot divided by W dot N. Q dot for our cooling, what we desired, over W dot, the power into it. Sometimes you put this over M dot, and then that was lowercase q, cool, divided by lowercase w in units of kilojoules per kilogram, and it's same units on both numerator and denominator. What is the relationship between this EER and the COP, refrigeration? To go back and forth between them, you need to know this unit conversion factor right here. You can either write it this way or this way. It's the same unit conversion factor. So 1 BTU per hour is 0.293 watts, or 1 watt is 3.412 BTUs per hour. If anybody's seen these yellow labels, EnergyGuide? So let's take a look at it. First of all, you see that the government, U.S. government, federal government, has specified the form of these labels, and they're standard labels for different pieces of equipment. Also, federal law prohibits the removal of this label So if you ever rip one off, you're going to be arrested. FBI or Secret Service will get you. Now, as soon as you purchase it, then it's good. You can rip it off and do whatever you want. Here is where the company puts the company name, the model number, and some other capacity information. But over here, the classification. So it's a room air conditioner. It has with reverse cycle and with louvered sides. This is an estimate of the cost range if you bought similar models to do the same thing. Put this in a room air conditioner. Some models would be down in the $59 per year, some up in $112 per year. This model is sitting kind of in a $98 per year. That's your anticipated yearly operating cost. Here is the energy efficiency ratio. Its EER is 9.5. So the energy efficiency ratio is provided. Notice that your cost, don't take this to the bank, this $98. Depends on your utility rates and how you use it. The cost range is based on models of similar capacity with reverse cycle louvered sides. Estimated operating cost based on 2007 national average electricity costs at around 11 cents per kilowatt hour, 10.65 cents per kilowatt hour electricity. So here's a question for you. If the air conditioner has an EER of 9.5, what is the COP? And you'll need to know these. You work it out on your piece of paper. Okay, so if the energy efficiency ratio is equal to 9.5, but we know that has particular units to it, right? It has units of BTU per hour divided by watt. We want to do some unit conversions. We know that the COP for the refrigeration has the same ratio of how much cooling was provided for how much work electric that came into the system. It's the same thing, but this is in watts per watt, dimensionless in that regard, not BTUs per hour per watt. So what we find is that the EER, if you multiply by the unit conversion of 1 watt per 3.412 BTUs per hour, that's the unit conversion factor, then the units will then be transferred over into the right units for the coefficient of performance for refrigeration. So we'll go ahead and substitute right here. This is 9.5 BTUs per hour divided by watt. You multiply by the unit conversion watt, 3.412 BTUs per hour, and you're left with, these cancel, the watts do cancel, and you're left with 2.78. So the COP, 2.78. Let's take a look at one of these yellow EnergyGuide stickers for a central air conditioning system. Now it's cooling only, and it's a split system. Hey, we're understanding this terminology. Split system, what's that mean? Outside unit, inside unit. Outside you have the condensing unit. Inside you have in the furnace essentially the evaporator coil, expansion valve, and fan. Okay. Notice XYZ, so it's just a made-up company. This is where a real company would put its information. Federal law prohibits, yeah. U.S. government approved, yeah. So here they have a seasonal energy efficiency ratio, SEER. Hold it, we just learned EER. Energy efficiency ratio. Now they have an S in front of it called a SEER. And that just means S for seasonal. The rest of it is the same, energy efficiency ratio. So it's calculated using the average temperature conditions where the temperature fluctuates. So they say sometimes we run it hot outside, sometimes cool outside. So this unit looks like it's coming in at around a 13.3. Energy efficiency range of similar models. So it looks like out on the market you could buy the least efficient would be around 11 or 10.9, and the most efficient 23 for the SEER in that range. And so you're looking at buying something on this scale. That's what they're showing you for this sticker. So the efficiency range based only on split system units, and it's based on standard tests set out by the U.S. government on essentially the condenser model, and it's combined with most common coil. Basically, they're testing what's outside the home. What's outside the home? The compressor, that's where you suck all the energy. Then you also have the fan and the coils. So those are the things that I showed a picture a couple lectures ago, how they've gotten bigger and bigger and bigger over the year, because larger areas, you can have a smaller delta T to reject that heat, and it's more efficient. So they're trying to improve the efficiency the engineers have over the last few years. Federal regulations take time to implement, and about 15 or 20 years ago, they set some benchmarks and said, no, in this year we're going to make this change, and in this year we're going to make this change, and in this year we're going to make this change. So in 2006, right, all the residential air conditioning units sold must have a SEER of at least 13. Used to be, whoa, I remember my dad bought one. Hey, I paid a little extra. I got a SEER of 10. Yeah, that was a long time ago. It was one of the first, to have a little sticker about the energy efficiency. Before that, it was like, who knows what you got? You just bought it by the reputation of the company selling. But anyway, it was a SEER of 13 was mandated that if they're going to sell in the United States, you had to have that. And to be qualified for Energy Star, the central air conditioning systems, typically split systems, have to be 14. Otherwise, you just got the base model, not a super Energy Star model, right? Now that requires that residential units manufactured after 2005 have a minimum SEER of 13, although the window units, the room air conditioners, are exempt from this law, so their SEERs or energy efficiency ratios are typically what's reported are around 10 or a little bit less. Starting when? When is this date? January 1st, 2015. A couple weeks away. Couple weeks away, right? Laws change. The split system central air conditioners installed in the southeastern region of the United States of America must have a SEER of 14. So these things creep in. What is the southeastern region? Well, Alabama, Arkansas, Delaware, guess what? Look at what's common in these. Well, they're in the southeastern part of the United States. Guess what? We have summer and summer and summer. Don't you have a lot of summer here? How about Alabama and Arkansas and Oklahoma? It's summer. So guess what? They've upped the ante for these regions because that's where you use a lot of air conditioning and a lot of energy is conserved. Now, the split systems that are installed in the other states, Minnesota, they use it for 2 weeks in the winter, the summer, and that's it. Their whole summer. It gets over 85, turn the AC on. And it's about 2 weeks. The minimum is still a SEER of 13. It doesn't jump up to 14. So that's a national requirement. Last year, the electric bill needed to run the air conditioning system was $3,000. Now, this is easy to say, but to really figure that out, because a lot of the electric bill goes to run your lights, goes to run your pool pump, goes to run your electric hot water heater, if you have that instead of gas, goes to run your stove. But only that amount of money to pay for the electricity to run the air conditioner was the $3,000. It was a SEER 13 system. The system needs to be replaced. It's been proposed. You're considering purchasing a SEER 18 SEER unit. Estimate the electric bill for next year if you purchase the 18 SEER unit. Last year, it was $3,000 for a 13 SEER. Going to be the new 18 SEER. What's the electric bill? Can you make that estimate? I'll give you a minute or two. All right, well, what is the annual cost to run a 13 SEER unit? It's going to be, well, depends on what is the cost of the electricity. So what I mean by the cost of electricity is this number for us is about 10 cents, 0.10 per kWh. That's our typical cost, 10 cents a kilowatt hour. A little less in San Antonio, but the national average, a little higher than that. But then you multiply by how much electricity that you used, true? How much electricity that you consumed over that time period, right? Well, what is our SEER? What was the definition of it again? It was how much cooling we achieved per the work or amount of electricity used, right? Is that our seasonal energy efficiency ratio? Right? So typically it was something big. Let's say this SEER, I'm going to subscript this. Like for a 13, we know then that ratio is 13. But so I can say that the work or how much electricity was needed to be provided, that's how much I had to go purchase from CPS. That's equal to how much cooling was needed divided by the SEER number of the unit that provided that cooling. Okay. Now this is where you start to get into assumptions. I'm going to assume the cost of the electricity doesn't change from year to year. Also, what else is going to stay the same? How much cooling you need for that summer. So one summer shouldn't be dramatically hotter than the other summer for comparison purposes. Okay. I can now substitute here. Let me write it down here. C13 is equal to the cost of the electricity times how much electricity I purchase, which is how much cooling I use over the summer, divided by the SEER number for that. And here I'm going to write that for 13. So I'm interested in the cost when I had a SEER of 13 compared to the cost when I have a SEER of 18. Same cost per unit for electricity, same amount of cooling, but I'm now having a different SEER number. I'm using a SEER of 18. I take this block right here and replace it because this equation, so I eliminate the cost per unit energy times amount cooling, and we find that the cost of the using an 18 SEER unit is for a year is a cost of using a 13 SEER unit multiplied by the actual SEER number 13 divided by SEER number 18, or substitute numbers. We had $3,000 last year using a 13 SEER. It's going to be an 18 SEER for next year. We anticipate the cost with the 18 SEER to be $2,167, somewhere in that vicinity, representing a savings of C13 minus C18 of $833, representing around a 28% reduction in your electric use or electric bill due to the air conditioner. Now, a lot of people will look at that 28% and they'll forget that $300 electric bill included lights, stove, hot water heater, pumps, other gadgets, right? And they'll expect a 28% reduction in the overall energy bill. That's a fallacy. The next thing they do is you have to think about this. What did you want to do with that brand new car that you just purchased? Park it in the driveway and look at it, or get it out on the road and drive it? And we confuse miles per gallon with the total gas bill for the month. You get a total electric bill for the month. So when you get a brand new air conditioner system, and typically you were complaining about not being comfortable in your home, guess what you do with that thermostat? You drive it more. You put it down a notch or two, and you enjoy the comfort in your home. So sometimes these people don't realize the real energy savings, even though they now have more comfort in their home. Heat pump. You'll see this EnergyGuide label on heat pumps as well. So let's take a look. Federal law prohibits, yeah. U.S. government approved, yeah. This is the company and the model number, but it's a heat pump for both heating and cooling, and it's a split system. So they can turn it around in the middle of the winter. The condenser unit is not acting like a condenser, it's acting like an evaporator outside. And the evaporator inside now acts like a condenser, and it supplies heat into your space. Well, notice they give you the seasonal energy efficiency ratio. Hey, this is around a 15 in a range of about 11 to 21. And they also give you a new metric. It's the heating seasonal performance factor, HSPF, heating seasonal performance factor. Its number is, for this unit, 8.2, where the least efficient 7 to most efficient 10 comparable models. So what exactly is this HSPF? It has the units of BTUs per watt hour or BTUs per hour per watt. So it's Q dot, not cooling, but heating. That's what you want. Divided by W dot, electric consumption, which you're going to have to pay for as it runs. So it's very similar units. Now we understand the coefficient of performance of the heat pump, true? What was that? Q dot heat divided by W dot elect. These looked exactly the same. It's just that the units are not the same. This is watts per watt, truly dimensionless, as we learned it and use it. This is BTU per hour divided by watt. So to convert back and forth again, what factor do we need? 3.412 BTUs per hour. So if you have you want to calculate the equivalent heat pump for the coefficient of performance for a heat pump, you take the HSPF value, which I'm just going to work out in units below, BTU per hour divided by watt, and you multiply it by conversion factor that the 3.412 BTU per hour is 1 watt, and now that will give you the COP of the heat pump. See that? So you take the numeric value HSPF, divide by 3.412, and you have the numeric value of the COP of the heat pump. So this one is 8.2. All right. Last year, the electric bill needed to run the heat pump was $4,200. So the cost to run for a year was $4,200 with a heat pump with a 7.8 HSPF. So I'm going to put 7.8. The system needs to be replaced. You're considering replacing it with a 9.8 HSPF system. Estimate the electric bill for next year. The cost for the 9.8 would be the cost last year with the 7.8 times the ratio of the heating seasonal performance factor of the 7.8 divided by the heating seasonal performance factor of 9.8, or just the $4,200 times 7.8 divided by 9.8. And that comes in at $3,343, annual savings of $857, which is a 20% reduction in electric consumption or use. Let's talk about gas refrigeration in the Brayton cycle. So if you run the Brayton cycle backwards, you can basically have two heat exchangers where one is you're absorbing heat at low temperature and dumping heat at high temperature. And it can act as a refrigeration system. How common are these? Rare. If you're doing refrigeration today, anywhere, most of the world, but especially in America, United States, it's vapor compression refrigeration. There is some absorption refrigeration. We talked about that. And there's some even smaller gas refrigeration. But how does this work? Well, you put something cool through the compressor. It's hot. Now that you cool it from 2 to 3, rejecting heat to a high temperature, and then you put it through a turbine. When you put it through the turbine, there's power extracted out of that flowing fluid to help drive the compressor, and now it gets very cold. And now it's able to absorb heat at a low temperature. Let's sketch it out on a temperature entropy diagram. We have 2 pressure lines. This is the pressure low, this is the pressure high. We start at state 1 and we compress to state 2. If it's isentropic, great, straight up. We then have the highest temperature. This is the high temperature right here at state 2. You cool it down to state 3. And then you expand it isentropically to state 4. That's the lowest temperature. 2 is the highest, 4 is the lowest. And now you're absorbing heat as you go 4 to 1. So Q in. And this would be Q out. This is a problem where the pressure ratio is only 4. It comes in at 100 kilopascal and 270 or negative 3 degrees C. Use constant specific heats. If you have isentropic efficiency for the compressor of 82% and 85% for the turbine, you can even have a little enhancement. You go 1 to 2S and then 1 to 2. So it ends up to be 430 Kelvin or 100 and almost 60 degrees C after the compressor. That's quite hot. You can reject some heat to that, away from that. Cool it down to about 42 degrees C. Expand it through the turbine with 85% efficiency, and now you're very cold at negative 45 degrees C. You can really provide some cooling. All right. Okay. What's the coefficient of performance for this system? Not very good, 0.6. What was the COP of the absorption refrigeration systems that I talked about that are in RVs? The water, the ammonia, and also the hydrogen. It's down 0.2, low, which means you burn a lot of propane to make it work. Okay. Or if you're going to use that electric power to make it work, you're just dissipating that electric power into heat and then driving the system. Not as good as using propane. But so this performance is better than the coefficient of performance of the gas refrigeration systems that are out there. But the coefficient of performance of vapor compression can be significantly higher. True? Much more efficient. Last question. What if that turbine, instead of being right here, you replaced it by an expansion valve? So I have a compressor, ideal gas. I have a heat exchanger. I'm going to reject heat. And I'd like to absorb some heat in this other heat exchanger. And it's an ideal gas going through the whole system. How's that going to work? Would it work okay? How would it work? So this is the one we talked about before. Let's say I start at the same temperature, state 1, this is the same. I go through isentropic compression in the compressor, same pressure ratio. I'm at state 2, I cool it off. I'm now at state 3, but instead of going through a turbine, I go through expansion valve. Where is state 4? It's not here anymore, is it? Will it be sloped over to the right? Okay, will it be like here? Okay. What do we know about ideal gases? PV is equal to RT. U is a function of T only, and H is a function of T only. Okay. So tell me, is H3 equal to H4? Okay. How does T3 and T4 compare? As you just showed me, T3 is higher than T4. Right? So what about what is the difference? Is T4 lower than T3? With the Brayton cycle, this is an ideal gas. This is the 3 characteristics of an ideal gas. So what about T3 and T4?
They're the same.
Who said that? Yep, they're the same. Thank you. So where's state 4 on this TS diagram? Because it's low pressure. Is this going to work? No. It will not work. It will definitely not work. Okay? So, yeah, you can look at a system, oh, that must work. It's close enough. Just a little modification, but it won't work. Right? This is not a refrigeration system. You must have that turbine. That turbine is what really drops the temperature by getting energy out of the air going through it from 3 to 4. Expansion valve does not get the energy out of it. And the temperature of a true ideal gas will stay the same. I'll pick up there next time. Thank you for your attention.